factory later. So, okay, so let's just start. So today we are very happy to have Chigusa from UC Berkeley. He got his PhD from the University of Tokyo, actually the same place as me, and then we have the same PhD supervisor, so I know him since that time. After he got his PhD in 2020, I guess, he stayed at KK for 6 months, and after that he moved to Berkeley. This fall, he's gonna move to MIT as a second postdoc, and then today he's gonna tell us about like automata and NB centers. So please.
Thank you for the introduction. Yeah, today's topic is this NB center, which is one of the quantum sensing equipment, which is applicable to many things, including the magnetic field. And today's idea of using this NB center for dark matter search is to look for the magnetic field-like signal coming from the dark matter using this NB center thing.
Junior, what does this NV mean?
Yeah, I will explain later, but it's substitution of nitrogen and vacancy. That is the effect. And this work is in collaboration with these people from QUP, which is a newly founded Japanese institute for quantum sensing. And although this paper itself is a theoretical work proposing a new idea, but we are now starting new experiments based on that idea. So let me start from a brief general introduction regarding the dark matter. I think many people agree with me that this dark matter is one of the most important hints of the new physics in the field of the particle physics. We have many observations, including, for example, galaxy rotation curve, cosmic microwave background, which suggests the existence of the dark matter. And also we know the relative abundance of the dark matter, or local density, local energy density of the dark matter. And all these observations are based on the gravitational interaction. So we know that dark matter has a gravitational interaction. But the many properties. Sorry?
Has gravitational interaction. What did you say? Sorry, I missed the sentence.
We know that
has gravitational interaction.
Has gravitational
interaction.
Yeah. But we do not know the strength of the gravitational interaction. For example, we do not know the mass of the dark matter. We don't know anything about the non-gravitational interaction, basically. So there are a broad parameter space of the dark matter, which is still allowed to us. And this is a sketch of the mass scale of the dark matter, still allowed in this stage. This plot is borrowed from the TAZ lecture by Tony and Lee. And this clearly shows us that still orders of magnitude mass range is allowed.
Is it really allowed? I mean, just to ask. If it's very light, I think, which means that will be cold, that destruction formation.
I think it depends on the production. Yeah, it can't be thermalized if it's very light, but there are other ways not thermal.
True. Today I'm.
So the strength of the direction is what you say, right? But so it's not only this; it's only the strength of the direction. So it's
yeah, of course, yeah, of course.
It's very light. It's weakly coupled.
Yeah, I'm saying that depending on the production mechanism and depending on the coupling, this mass range is probably allowed. And we, of course, we have to think about the model building, for example, to explain that.
So what I say is that it's not only a mass; it's only the strength of the interaction with the rest of the plasma, which gives you if all these rates is allowed or not.
Yeah, I don't say that all these range with arbitrary coupling dark matter is allowed. We have to think about the mechanism to create the dark matter relative abundance. Today, I'm gonna focus on the so-called misalignment mechanism that is applicable for this ultralight dark matter range. Okay, yeah, as I mentioned, this is the my focus today. In particular, if the mass range is really light, then it turns out that the occupation number of the dark matter required to explain the dark matter relative abundance is much larger than 1. So in this case, the dark matter behaves as a classical wave. So that's why this range of the dark matter is called wave-like dark matter. And an example contains like axion or dark photon. And even if we constrain ourselves to this range of wave-like dark matter, still there are 20 orders of magnitude mass spread, which is still allowed. So somehow we have to construct different ways to look for this broad mass range in order to search light dark matter signals. And as I mentioned, this is a mechanism of the dark matter relic abundance production I'm focusing today, the so-called misalignment mechanism. In this mechanism, we consider a classical field of the dark matter, which is oscillating with the frequency of dark matter mass. And so this is the mass of the dark matter, and there's a small space dependence according to the velocity factor. And basically, this delta is the oscillation phase. And this is basically the expression for the classical wave. But because the coherence of the dark matter parameters are maintained only within the wavelength scale, so after we wait for coherence time, like 1/mv squared, we lost the coherence of the signal, and some different oscillation phase, different velocity of the dark matter is observed at the laboratory. Okay, then then the idea of this mechanism is that this oscillation itself contains some amount of the energy density, which actually explains the abundance of the dark matter in the current universe. Then the question might be that how we can detect such an oscillation signal. Let me focus on, for example, the axion dark matter. If we consider dark matter interaction with standard model fermion, then this oscillation might affect something at the laboratory. And for the case of the axion, for example, the interaction is given by this pseudo-scalar type interaction. In the non-relativistic limit, this gamma mu gamma 5 operator is rewritten in terms of the spin operator. Then, because this interaction Hamiltonian looks very similar to the interaction of the ordinary magnetic field with the spin operator, so this factor in front can be rewritten in terms of the effective magnetic field.
Excuse me, F is a fermion field, right?
Yes.
F small.
F small is the fermion field, yeah, standard model. I will focus later on the electron, neutron, proton. But okay, yeah, that's the target particles. Okay, then according to the fact that the axion field is oscillating with a frequency of mass, this magnetic field also has a frequency of mass, and its amplitude is proportional to the coupling of the axion to fermions. So if the coupling is very small, like 10 to the minus 10 as a typical value, the amplitude of the magnetic field is also small, like at Tesla level. So in this case, our task is something like this. We need a detection method of this very weak magnetic field at Tesla level, for example, with a high sensitivity. And at the same time, we need a broad frequency coverage to look for broad mass range allowed for this wave-like dark matter.
So this dark matter, since it's so light and we pick up and like action, as you say, I assume it's thermally produced, right? It's a thing.
No. It's not summary.
Actions are thermally produced.
No, I'm not saying that the energy density of the part.
How is that what is produced?
I mean that
How can we get the abundance?
in this mechanism, the dark matter energy density is contained in this oscillation of the classical field itself.
Okay.
So the picture is not like dark matter is a particle, but dark matter behaves like a wave. And this oscillation energy explains the.
So it's not like action then, because action is thermally produced.
I think it is one.
No, you can produce action thermally, right?
So I'm not writing on the classical field. You can have some field power in the other.
You can have a fluid like this, but use the action are thermally produced.
If you're talking about the heavier axion.
No.
He's talking about like very, very light.
Yeah, from fraction the constant is really.
Yeah.
Independent of the mass, the mechanism is really, I mean, you have to do the thermal calculation. Kaput is not here, but this is exactly that exercise we're doing. Anyway, go ahead, I mean.
Okay, yeah. Let me define my axion as a general pseudoscalar particle, which is this kind of fermion interaction, and which is described by this classical wave. And then this is proved that this can successfully explain the dark matter radical abundance. So, okay, anyways, this is our task. And one of the possible way to think about this high sensitivity, broad frequency coverage magnetometry, I would like to propose to use the energy center actually in diamond. So this is the outline of my talk today. From now on, let me start from the brief introduction to the energy center itself, because I think I need to introduce, starting from what the energy center is.
What these letters N, V, what what they abbreviate?
Yeah. Next slide. Let me do that now. Sorry for keeping you waiting. This is the energy center. We consider lattice defect in diamond, and as you asked, N is the abbreviation of the substitutional nitrogen inside diamond, and V is the vacancy in diamond,
Okay.
which means that there is an absence of the carbon atom at one of the lattice sites around here. Both of N and V can exist as isolated lattice defects inside diamond, but it is known that once N and V form a bound state, it is much more stable than the individual N and V. That's why we often observe the NV complex inside a diamond lattice, even in the nature. This pink diamond is actually an example of the NV-rich diamond lattice.
But out of curiosity, when you say that, for instance, N is not stable on its own, like what happens to the N?
I mean, I don't say N is not stable. N is stable itself, but once we the binding energy for N and V is negative, and it can form that bound state.
Okay, like the N will float around itself, finds a V.
And how this N will get inside of the crystal made of Cs, right? It's carbon-like.
True.
And all of a sudden, one node of this crystal becomes nitrogen. How it comes? How do we do it?
Are you talking about the one electron remaining compared with the carbon atom?
How do you manufacture it?
Okay, in order to manufacture it artificially, we have to inject the nitrogen beam into the diamond. Then it can create the vacancy at the same time because of the high energy collision. And once after the annealing of the lattice, we form a lot of NV centers.
So the picture is like you shoot a nitrogen beam and you get vacancies, but they are in general at first, like they are not bound state or something, but they float.
True.
Then,
At higher temperatures, they can freely move around.
How are you sure that you'll get the same number of nitrogen as vacancies?
I'm not sure. The dynamics is complicated, and only reason why we expect a lot of number of NV center is that the binding energy is large, and NV is so stable that we can easily form them.
Okay, so it's possible there are some N's floating, like leftover N's floating around.
There should be some other types of the defects, a lot of them, and actually it limits the relaxation time of the spin system I'm focusing on from now. I will come back to that point later. Okay, for the sensing purpose, this NV minus is the target complex, where two extra electrons are localized at the position of vacancy here. Then, because there are two electrons, they can, their orbital angular momentum and spin angular momentum have several different combinations. But in the lowest energy levels, it is known that they form an orbital singlet and spin triplet, S equals to 1. And for the magnetometry purpose, this spin 1 of the electron system is the target object I'm looking at. Okay, now let me explain how this system works very well as a quantum sensor. The key idea is to use the fluorescence readout of the quantum state. The statement is, by using the fluorescence measurement, it allows us to read out the electron spin quantum state. More precisely, this mixing angle theta is what is read off from this measurement. Here, 0 and the plus minus state corresponds to the eigenstate of the z direction component of spin operator. Because we are now thinking about the spin 1 system, there are 3 states, 0 and plus minus 1. Let me just for simplicity neglect plus state. And if you consider the system composed from 0 and the minus state, then there should be some mixing angle between them. This theta information can be laid off. What do we have to do? This is the fluorescence. We irradiate the diamond sample with this green laser light. Some red light comes out from the sample. We measure the amount of the red light.
So just to understand, so you have the diamond, you say because of the absence of the nitrogen, you have localized electrons inside the diamond. This is what you say, right?
Yes, yes. 2 electrons are localized at the position of the
I
vacancy.
mean, the wave function is really localized in this.
It seems so.
Really?
Localized and isolated from the environment. That is the key.
Spins are compensated. There's
I
a
see.
place where you have a spin.
Yes.
Only 0 spin.
Yeah, thank you for that question.
And the plus and minus 1 states are degenerate but higher than the 0 state.
Yes, that's the this part. Yeah, let me explain about that. This is actually the energy levels of this 2 electron system. And as you asked, this is the lowest energy levels B1 system. And this splitting between the 0 and the plus minus 1 state is the so-called zero field splitting, 2.87 gigahertz, coming from the self-interaction of the electron spins. And also there's an energy split between the plus and minus state coming from the Zeeman splitting if we apply a magnetic field along the z-axis. This is the lowest. All the other excited states are coming from the different combination of the orbital angular momentum and, spin angular momentum. Like for example, this is the orbital triplet, this is the spin singlet states. Once we irradiate the diamond sample with a green light, then these states are excited to higher state and coming back with some kind of relaxation. But there are 2 types of the relaxation path, like the direct relaxation with red light coming out, and the indirect 3-step relaxation, where the energy gap is small enough such that the coming out light is infrared in this case, instead of the red light. So depending on the path, the wavelength of the light coming out is different. And the key point is that depending on the initial state, like if we start from the 0 state, or if we start from the plus minus 1 state, the probability at which the direct relaxation happens is different. That's why, depending on the initial state, we have a different amount of red light coming out. So measuring the amount of the red light tells us about the initial mixing angle.
You took 2 spin 1/2 states and you combine them to get a spin 1 state with 3 levels. Like in principle, you could have also gotten a spin 0 state.
That's these 2 states. These 2 are spin singlet orbital triplet states, and this is the spin singlet orbital singlet.
Oh, okay. So some of your NV centers are in the spin singlet state, but the one.
Yeah, some might be, but it's highly excited. So I don't know. Yeah, it's highly excited. So in the ground state, at least, they should be in this region.
Is there any reason to see why that's the case? Because I usually think of the singlet as being like lower energy than.
Let me remind myself.
There is a Punzu that tells you that the lowest energy configuration corresponds to a highest spin in the inside an atom, The highest.
Mm,
they
I see.
change-
That's
they
right.
change,
That's
the orbitals have to add to the highest orbital. It's, it's like crazy.
Mhm, mhm. Yeah, that's one example.
Oh,
Absolutely.
It's German, so who's.
I see, I see. Actually, yeah, in the later part of this talk, I'm gonna talk about the use of nuclear spin in energy center instead of electron spin. In that case, that Hund's rule is really important to calculate the axion interaction with nuclear spin.
Different coupling, nuclear, I'd say JJ coupling as opposed to LS coupling, so that there is like the individual spins of the nucleon, L, and the spin of the different nucleons for person together.
I guess I'm gonna talk about a little bit about that kind of topics. Thank you. So this is the main, how to say, idea of how the energy center works as a quantum sensor. As a result, it works as a multimodal quantum sensor, which is sensitive to basically everything, like temperature, electric field strain, magnetic field, and regarding magnetic field, I will explain later, of course. Several benefits of the energy centers are in order, like sizable relaxation time of the spin quantum state. This is actually the result of the isolation of the two electron system from the environment. So even at the room temperature, this spin system is hardly thermalized, and 1 microsecond relaxation time is achieved. Another benefit is the wide dynamic range or broad frequency coverage. About this, I will explain from now on, but there are several different protocols we can use with energy center to look for different frequency range. So yeah, it is one of the benefits, and it is, of course, suitable for the light dark matter search.
Excuse me, when
Yep.
jumping ahead of you.
Thanks.
The magnetic fields which you would expect to get from, let's say, ultralight axions are very weak, right?
Yes.
So is your device will be able to detect such a weak magnetic field?
Basically, our idea is to accumulate the statistics of the information. One thing is by increasing the number of energy centers, and the other thing is to observe for a long time duration, like 1 year, for example. That's the idea.
But in general, the atomic magnetometry has reached the level of speed magnetometry. It's just or use some other systems, and they can go down to 10%.
Yeah, that's right. Yeah, for energy center too, like I forgot, 100 femtotesla or something sensitivity is already achieved. Yeah, as I mentioned before, this ensemble of energy centers is good to enhance the sensitivity. And the point here is that because we are now thinking about the crystal condensed matter system, if we fix the concentration of the energy center like 1 ppm, 10 to the minus 6, the number of the energy centers are increased proportional to the Avogadro's number. So 10 to the minus 6 times Avogadro's number, like 10 to the 17th, 18th number of the energy centers can work as individual magnetometers. So we can, I think, relatively easily enhance the sensitivity with statistics. Okay, now then let me turn to the DC magnetometry. Here, I would like to explain how we can use energy center to look for DC-like time-independent signal. Okay, for that purpose, one important thing is to manipulate the spin quantum state. And this explains how we can manipulate the system. The so-called Rabi cycle is important. What we do is to apply some transverse driving magnetic field from outside, whose frequency exactly matches with one of the energy gaps. Say, for example, if we pick this 0 state and the -1 state, And then the corresponding frequency is described by this expression. And if we apply such a magnetic field, it causes a resonance transition between the 0 and the minus state. The time evolution of this cycle is given by this expression, like superposition of 0 and the minus state, where the mixing angle given by the amplitude of the magnetic field and the time duration for the lab cycle. There are 2 comments, I think, regarding this. First of all, we have to use the transverse magnetic field for that purpose, of course, because only the transverse component of the spin operator connects different spin modes, like a 0 mode and minus 1. If the magnetic field is along the z-axis, we cannot do that. And second point, by choosing one of the frequency, like this expression, the remaining state, plus state, is completely out of the dynamics.
So you have point transverse, you don't have longitudinal magnetic field and state?
We don't have. This is just a applied magnetic field. So
So you tune it like we have.
There is,
Yeah, yeah, yeah.
minus 1 plus 1 is,
Right.
it means that there is a constant magnetic field on top of.
oh yeah, true. Yeah, this is a constant one.
Oh, it's like,
True.
it's like an MR.
Yes, it is.
Yeah, true.
And BZ is the thing we're trying to measure here.
BZ is again applied magnetic.
So the transfer perturbation unit is
Correct, yes, it's much.
So my picture is that the BZ is also applied, but on top of that, there's some anomalous component of the BZ coming from the axion, for example.
the resonance.
Mhm,
The
mhm,
resonance.
mhm. Yeah. I think that's the.
So you're gonna basically tune the Y until you get this exact resonance to compensate for the anomalous component of BZ.
Sorry. Yeah.
So it's not BY, but F, no?
Which one?
Sorry, yeah, maybe also the same as.
Oh, yeah.
If you want to measure BZ, then you want to kind of change the frequency.
Yeah.
That's not the idea. I will explain. Finally, the DC magnetometry is a combination of the lab cycle and the free precision. I will explain later. Yeah, let me continue. Maybe that's the good way to explain it. Maybe you will ask 10 minutes later. Okay, in order to continue, let me briefly explain the useful illustration of this case. As I mentioned before, now we already neglected one of the state, plus 1 state. So this whole system can be regarded as an effective qubit system, consists of this 0 and minus state. And this kind of qubit system is well illustrated by the Bloch sphere. This is that it is. And this is a Bloch sphere is the mapping from the general qubit state to a point on the sphere S2.
So what do you want to be the two-state system?
I mean, as a driving field, we only apply the field with this frequency. Then the dynamics, if we consider the time evolution of the quantum state, this plus 1 state is totally unique. That's why we can neglect this state and we can treat the whole system.
Yeah, so it's two-state system, right?
This is, yeah, true.
This qubit means something else, maybe. I don't know.
I mean,
Got some information behind it, some reduction, maybe.
Yeah, possibly. My definition here, sorry, is to think about the two-state system. But the fact that the Bloch sphere is useful for this two-state system is correct, I think. And here we map from, for example, this mixing angle theta is mapped to the polar angle on the sphere, and this relative phase factor phi is mapped to the azimuth angle. So as special points, for example, we have this ground state, which is mixing angle equals to 0. This excited state corresponds to mixing angle equals to pi. So this is it. And on the xy sphere, sorry, xy plane, what do we have? Theta, mixing angle theta is half pi. So the weight for superposition is like the same 1 over square root for both 0 and minus state. But because the rotation around the axis corresponds to the relative phase factor, the point on the x-axis and point on the y-axis differs by a factor. Then what Rabi cycle looks like on this sphere? This proves us the usefulness of this cross sphere. If we apply a magnetic field along the y-axis, which is oscillating with a specific frequency, the Rabi cycle is given as like this, just a rotation of the quantum state around the y-axis. This is consistent with the expression I have given. Right? This is the rotation angle given by Rabi cycle. Theta is proportional to time. So as a function of time, like this. And one comment, the reason why it is rotating around the y-axis is, of course, because we apply the magnetic field along the y-axis. If we choose the x-axis instead, then the quantum state should rotate around x-axis. In terms of the quantum computation, this corresponds to the Rx, Ry rotation gate acting on a qubit system. And because we have both Rx and Ry, by combining those two, Ry, Rx, Ry, we can construct any arbitrary SU2 rotation acting on this quantum state. So this energy center system has a total control on the qubit state. Let me do another exercise on the Broad sphere, and this free precision is actually important for the sensing purpose. What happens if there is some anomalous magnetic field along the z-axis, as I mentioned, to the state? Let's start from the point on the x-axis and guess what is happening. This is what is happening. Of course, the quantum state rotates around the z-axis. But the dynamics underlying is a little bit different from the Rabi cycle. What is happening? According to the existence of the magnetic field along the z-axis, there's some anomalous energy difference caused by this magnetic field, just as similar as the Zeeman splitting. Then, because the evolution operator of the quantum state is given by exponential of IH, and H can be substituted by the energy eigenvalues, there appears some anomalous phase factor after time duration of tau. And this is the expression for a phase factor after waiting for time duration tau. This is basically the integration of time equals to 0 to tau of the signal moment. And
okay, so for instance, like this BC in principle can also change the resonance function, right? But here you can't ignore it because it's just irrelevant. It's just so tiny. So that
you are talking about the transverse component of the axion. Sorry. Okay. I see.
So this one, and on top of that, you also.
You're talking about the energy.
Yeah.
And,
come back to our question before.
Yeah. Actually, that is the key why we can detect this signal, I think.
Okay, this phase difference is actually.
Yeah. Now, here I'm working in the interaction picture where the unperturbed Hamiltonian is defined by the applied magnetic field only. So there's a little deviation from the actual energy difference and the unperturbed Hamiltonian I'm using. And that difference actually makes this phase factor in the end, if we work in the interaction picture. But basically, that's just a discussion of the picture. And in the interaction picture, this kind of understandable dynamics is observed.
That would be the same length picture, right?
Yeah, that's just a discussion of the picture. So, yeah, anyways, it's okay. Okay, one point here is that this expression itself is irrelevant to the signal frequency. However, large frequency is acceptable in this expression. But at least you can say that if the signal is fast oscillating, meaning that the frequency is much larger than 1 tau, then there's a cancellation. So this phi tau is sensitive only to the DC-like signal, like the frequency much smaller than 1 over tau, and then the phi tau is given by the oh, sorry. And sorry for keeping you waiting. This is the conclusion, what we do for DC magnetometry. lambda sequence so-called is a combination of the Rabi cycle, free precision, and fluorescence measurement in order to be sensitive to DC-like signals. This is it. First, we start from the half-pi pulse. Sorry, it is a little bit fast, but start from the half-pi pulse to transform the ground state to the starting point of the free precision. We wait for time duration tau. It makes the phase factor here. And afterwards, we perform another pi pulse around the x-axis. Then what happens at the in the end is that this phase factor accumulated by the signal magnetic field is converted into the population difference or mixing angle information. And this is the key because the phase factor is relatively more difficult to observe. But the population difference or mixing angle information can be let off by using the fluorescence measurement. So in this sequence, the final signal estimate is proportional to the phase factor I have acquired during the pre-precision. And this is the expression. It seems like the longer tau is better. To some extent, it is correct. But there's a limitation coming from the relaxation time of the spin. So tau equals to 1 microsecond in this case is the optimized choice to maximize the sensitivity. And because it is important later, let me briefly comment on the dominant source of the relaxation, dephasing. Dephasing comes from the existence of the inhomogeneous magnetic field. And the source of the inhomogeneous magnetic field is like, sorry, is there a question? The source of the homogeneous magnetic field is the stress on the diamond lattice or other defects other than the energy center, as we mentioned, which might have a nuclear spin distribution like the carbon-13 instead of the carbon-12 have a nuclear spin of half, and it can affect or contribute to the homogeneous. Then under the existence of such a field, the evolution of the spin state for each energy center is highly site dependent. And after we wait for 1 microsecond, typically, the coherence of the signal is low and exponentially. This is the sensitivity plot for DC magnetometry. This is the system as a function of the axion mass and coupling. Because we are now using the electron spin, there's the axion coupling with electrons, of course. 3 different colors corresponds to 3 different setups. And number of the energy center, n equals to 10 to the 12 is the more realistic setup, which is already achieved. Laboratory, n equals to 10 to the 20 is more challenging. But thinking about the concentration of n, we possible. The observation is total observation time. As I mentioned, the each Ramsey sequence takes, roughly speaking, 1 microsecond. So if we have 1 second observation time, we can repeat the measure into the 6. Then it can enhance the statistic of the coupling. I mean, they actually currently constraint. The biggest constraint coming from the red giant. So, to be honest, this coupling above this line.
What did I do?
Sorry? Could you
No,
repeat?
excuse me, I'll turn it off.
Oh. Okay. All right. And yeah, this is the 1 second. These 2 lines corresponds to 1 year observation. And maybe two features of this plot might be split.
This is the number of the samples. 10
Yes,
to
10 to
20.
12, 10 to 20.
So how many are currently maximum?
This one, 10 to 12. And but one comment here is that this going to higher sensitivity with using larger diamond is a completely new direction in the context of the energy center magnetometry. So there should be many challenges towards that direction, but it should be studied in the context of the axion, for example.
So this is from the theory, right? The calculation.
From the theory.
And why do you have these windows of the?
This comes from the integral of this one. Going to higher frequency, there's the oscillation. Mhm. So yeah, basically we do not have sensitivity to these regions. Yeah, that's one comment. Because this is sensitive to the DC dark region, 1/tau corresponds to megahertz frequency. So the sensitivity is flat for megahertz region below megahertz, but above megahertz we lose the sensitivity.
So I understand that part kinks, some of the lower kinks are coming from.
Yeah, this comes from, this is the second point. This comes from the coherence time of the axion. Axion coherence time equals to 1 year corresponds to this mass. And above that, the coherence time is then the increase of the sensitivity as a function of observation time is looser, I mean smaller, to say. Yeah, it is more difficult to increase the sensitivity.
I think you also, in this model is we have, we need the dark matter particle that comes to the magnetic field, that's it, right?
That
To spin.
Spin of the magnet.
Yeah, effective magnetic field coupled to the electron spin only is the signal.
Why is the purple line like positive?
Yeah, and this thing, it corresponds to the frequency below hertz, roughly speaking. So for 1 second observation, the axion signal does not oscillate below this region. So if you are very unlucky, it is possible that you do not observe anything, even if the coupling is something like this.
So there are constraints on this plane already from the existing helium-3 potassium combinatoric system, right? It would be fair to plot it so we know where this line is.
Oh, sorry. Yeah, for this electron coupling, I haven't.
Because it compares potassium and helium-3, so the potassium has spin.
Yeah, as far as I remember, their constraint is more stronger for nuclear spin, neutron spin. But yeah, there should be some line corresponding to it. And the mass range is something. Yeah, I agree.
So it's above or below? Above.
It's a question. It's not, I mean, I would imagine that it's more sensitive on that than 6.
Yeah, for later discussion about the nuclear spin, I will show you the mass range that magnetometry is sensitive to, and yeah, let me discuss it later.
I guess sort of related. So you did the thing where you had like 2 unpaired spins makes like a triplet state, but then I like get rid of one of the states, so I'm back to a 2 spin state. Like is there a reason why this idea is better than just using unpaired spins to begin with?
You mean unpaired spin? What do you mean? Sorry, I don't
Like
get the point.
Something with like 1 unpaired rather than needing like 2 unpaired electrons that combine.
I don't know if it is related to the paired nature of the system, but one thing is that the system itself is isolated. That's why the relaxation time is really long in this case, like 1 microsecond. And I don't know many examples that it's possible to achieve that long relaxation time for electron spins. I don't know, yeah.
Confirm the purple line. Below 1 second, you draw dash lines because there's a chance you are unlucky that
Yes.
happen to have 0 amplitude at your device.
Yeah.
Although normally I would expect there's some amplitude. You should still be sensitive.
That's right.
You
So
just, want to indicate you are unlucky.
yeah. So the interpretation of the line is a little bit different for this range. This should be interpreted as I don't know how to say 68% confidence level for not observing anything or something like that. So yeah, but that's basically the meaning.
Does it also depends on gradient of the axion, the direction of the gradient of the axion, like you say like DC?
Yeah, also true.
So you do have some specific direction that you are sensitive to as a whole.
That's right. That's right. And yeah, the axis is differently defined by the axis of the energy center, N and V. Here is a diamond lattice, and there are 4 specific directions, right? If we put N and V here and here, then this direction is defined as a Z direction.
Like this N 10 to 12, like they can actually have different directions or something. So I was wondering whether, so for each NV center, you have Z axis, but that can be defined for different NV centers that you're using.
There are 4 different possibilities, only discrete.
So then maybe, even if the axion itself is coming in this direction, then some of them are not sensitive, but some of them sensitive.
True. Yeah, from the first.
Worry about unluckiness.
Yeah. From the first place, we can apply the magnetic field, whose direction is not correlated to this lattice direction. Then in this case, the frequency for Rabi cycle is different for 4 different directions. So we can, for example, use only one direction to look for the signal, for example, or maybe we can apply some similar idea to the vector magnetometry, which is sensitive to the components of the magnetic field. So we can do many things.
Really, you're only using like a quarter of the NV centers.
Yeah, literally speaking, yeah. Quarter is the possible factor we have to take account of.
Write this N here, is that?
Yeah, maybe 4 times 10 to the 12 corresponds to this line, possibly. Yeah, I agree. So I don't know how much time I. Yeah. Okay, so let me just jump to the AC magnetometry. I have to explain about yet another possible way to look for different frequency range. One is this AC magnetometry, which is maybe this one. As I mentioned before, if the signal is oscillating, there is a cancellation in the Ramsey sequence. Then there is a simple cure to be sensitive to this kind of oscillating signal. That is to say, put one pi pulse in the middle of the Ramsey sequence. Then this is the so-called Hahn-Echo sequence. Then what happens is that according to the pi pulse, the effect contribution from the oscillating magnetic field is reverted for the first half part and the second half part. And if the signal itself is oscillating, then positive and negative reversed contribution constructively accurate. In terms of the expression, we have this kind of difference of the first half integral minus second half integral is the final signal. But this is, of course, some targeted protocol targeted at the specific frequency 1 over tau instead of the broadband search for the Ramsey sequence. But here is actually one benefit of using this kind of protocol that is related to the fact that any DC magnetic noise effect cancels out if we use the additional pi pulse at the middle of the sequence. As like this, the first half part and the second half part cancels with each other. Then this cancellation is also true for the inhomogeneous magnetic field. That is the dominant source of the diffusing effect that limits the relaxation time for Ramsey sequence. So this is the dynamics of the LB quantum states. Each arrow corresponds to the quantum state of the each NV center. And according to the dephasing, there's a spread of the arrows as like this. But at the position of the echo, we have actually this, again, meeting. Coherence is back. And by measuring the quantum state at this point, we can recover the coherence. This, I say. The corresponding relaxation time is much longer than the decoherence time scale, like 100. So using this protocol instead, we can be sensitive to the targeted frequency 1 over tau equals to 10 kilohertz. But at this point, actually the sensitivity is better, much better than the Ramsey sequence because of the longer relaxation time. And there are actually some complicated dotted lines corresponding to different choices of the setups. Like for example, we can artificially take a shorter time for pre-precision, tau equals to 10 microseconds, for example. Then the target frequency is set by an order of magnitude. So the 100 kilohertz range can be looked for. And also, this is related to our experimental setup, but it is known if we go to the cryogenic temperature, then the relaxation time becomes longer. And then by using some different setups, also by increasing the number of pi pulses, we can also make the experience time longer. We obtain this envelope of the sensitivities. I have to stress that we cannot prove all the parameters about this with one fixed setup, but for any point about this line, we can consider some kind of a setup, experimental setup that is sensitive to this. That is the meaning of this plot.
You require scan to achieve this line or not scan this?
I mean, this line is just one experimental design, but yeah, this one, of course, is a scan.
And what's the time you put in there? What's the assumed time?
I mean, yeah, I don't want to say it's a scan, but because it's a total observation of 1 year. So what I mean is that if you are interested in this point, for example, specifically, then there's a way to. So this is just for.
So each point is 1 year of time for a single frequency, resonant frequency.
So yeah, this is a little bit different from the sensitivity plot, but I would like to demonstrate that it has a possibility to look for several orders of magnitude, different frequency range by choosing different kind of a setup. Yes, it's less than 10 minutes left. I don't know what I have to talk about. First, I want to also stress that this is one kind of the quantum sensing technique. So there are many possible applications of the involved quantum methodology techniques. And this is just an example. We can use the entanglement of the quantum states, for example. The idea is to use the so-called GHG state. That's something like this. This is an n-qubit extension of the Bell state in some sense. And if we use this state instead of this one, what happens after the free precision is something like this. Instead of acquiring this phi phase factor, we acquire n times phi factor. The reason is simple. The energy gap between 000 and 111 state is enhanced by a factor of n. N is the number of qubits entangled with each other. Then this n times gain is actually at the level of the amplitude. So at the level of the signal, in some sense, n to the squared gain is possible. It should be compared with the naive n times gain of the sensitivity if we accumulate the statistics classically. So yeah, additional factor of n is possible. Yeah, that's a good point. We have to be careful with the noise effect because some kind of noise cancels the benefit of this kind of approach. That's a good point.
How can you make this state? I mean, can you construct it?
I mean, if you can really perform the quantum game, then this kind of game actually.
Please understand. I mean, going back to the example you had with electrons,
Mm-hmm.
instead the diamond. How can we realize this thing?
I see. Yeah. Speaking of NV center, there seems to be a way to make I don't know 2 qubit entanglement, for example. I don't know the way. Sorry. Yeah, that's related to my next comment. It is really ambitious to make for example 10 to the 12 NV center entangled with each other. That is a hope, of course, but it is a little bit difficult. So My comment here is that theoretically it is an interesting direction, and as you asked, there's some discussion to be done related to noise effect and something like that. So I would like to start this kind of direction, and also consider how to practically make this kind of state. I don't know what is happening. Maybe 5 minutes or so. Let me briefly discuss the recent development regarding this project using nuclear spins, time arrows.
Well, before you go there, so the DC, like constant quasi-magnetic field.
Mhm.
Can you actually do any progress without the Comagnetometry, just with the, like usually if it's in other fields, you have to have like two species that you can factor out the fluctuations in the background magnetic field. And only then can you make a statement about something that is there. So is your scheme using Comagnetometry somehow?
Not yet. I'm gonna talk about the Comagnetometry protocol I can propose to you, but not yet.
But how did you come up where you had this, in the DC part, you had the sensitivity?
Oh, that sensitivity plot is based on the assumption that the noise is dominated by the spin projection noise. There's no magnetic fluctuation effect included.
Well, it's for a reason that nobody has any kind of super precise measurements without two species, right? It's just, it feels like without my Comagnetometry.
Yeah, I think I agree, and I'm gonna talk about the Comagnetometry soon, and also maybe there needs measurement to identify the source of the background, like we are doing for the photon-based experiment, for example. But I basically agree. I don't know. I can get to the Comagnetometry. Yeah. Okay.
I think there was something, but they didn't. They didn't look good. So I think that they're moving to the same.
Okay.
Maybe.
Yep. I will be in 5-10 minutes.
Well, we book this room until 2, so.
Oh, okay.
Yeah,
Thanks. Yeah. The idea of using nuclear spin is that the axion interacts with electrons, but also to neutron, proton, other species of the fermions in general. So even if we have an experiment sensitive to the axion electron coupling, it is worth doing yet another experiment based on the axion nucleus coupling, for example. And so then fortunately, there's a nuclear spin in energy center system coming from the nitrogen-14 spin. So if we can use it for quantum sensing, it is very good. But then there might be some question regarding how we can do that. The question is, kind of reasonable, because the nuclear spin only weakly couples with the magnetic field. And so how we can manipulate it, how we can measure it, that should be a question. But then it turns out that according to the existence of the hyperfine interaction between nuclear spin and electron spin, it is possible, actually. Let's see, this is the energy levels of the two spin system, electron and nuclear spin. For simplicity, we have already picked up two of the nuclear spins, like a plus state and 0 state. This is effectively a 2 qubit in my sense system, and the energy levels are given by this. Without the hyperfine interaction, the degeneracy of the energy gaps are existing, like this is delta and this is delta, but with a factor, there are difference of the frequency, so it is practically possible to pick up one of the frequencies, like delta, to perform the Rabi cycle, to perform the rotation between these two states only. This Rabi cycle does not affect these two. In this sense, this manipulation corresponds to the controlled RY gate acting on the electron spin qubit. Similarly, we can do the same for the nuclear spin state with this Q frequency, for example. It corresponds to the controlled RY gate acting on the nuclear spin state. And the only difference practically is the typical size of the frequency. Here, the frequency is roughly speaking megahertz instead of gigahertz. So some radio frequency application is needed, but it is practically. Okay. Then by combining these two, we can do everything basically. For example, the RX high rotation corresponds to CNOT gate. So by combining CNOT gates and SU2 gates, we can make general SU4 rotation onto this two qubit system. Regarding the measurement, we can perform the controlled NOT gate, mapping the nuclear spin state onto the electron spin state, and the preceding measurement of the electron spin state indirectly measures the nuclear spin state.
Have people actually done this nuclear spin rotation?
Rotation, yeah, should be. Yeah. For example, this paper is doing this measurement of the nuclear spin, which is composed from CNOT key. This is the rotation I have mentioned before. So combining these two, we can basically do anything. Nuclear spins of the nitrogen-14 should be able to use for quantum sensing in the same way as the electron spins. Then I think I can skip this part. But the point is, before going to the sensitivity plot, one comment here is that how the axion interacts with the nitrogen-14 spin. This question is again reasonable because the ordinary magnetic field couples to the spins of the fermions plus some orbital angular momentum of the charged particle. But the axion only couples to the spin of the fermions. So the interaction with the nuclear spin might be a little bit different. In order to calculate the axion interaction with the nuclear spin, we have to know detail about the nuclear composition. And here is the nuclear shell model description of this 14 nitrogen atom. Interestingly, this 14 nitrogen is one of the rare stable odd autonuclei, which has odd number of neutrons and odd number of protons. So they have contributions from both the neutron and the proton spins to the magnetic bond. This is the description. 1 ampere neutron, 1 ampere proton in this 1p1/2 orbital is the composition of the nuclear spin. Then from this, through this kind of little algebra, we obtain this combination of the axion coupling that couples to the nuclear spin of the 14 nitrogen. This is the linear combination of the axion neutron coupling and the axion proton coupling, simply because of the fact that the symmetric combination of the neutron proton spins are existing inside it.
We have to do something like that very recently. And we've got the same factor, and the literature contains all sorts of wrong spin factors, like 1/2. You took the spin line by equally with the neutron and proton without thinking.
Yeah, I can. Yeah, thank you. I can discuss later about that. That's a good thing that this calculation is confirmed to be correct. Anyways, the important thing is that this combination appears, and we can obtain the translate on this Fa tilde as a function of axion mass, and something like this. And okay, the one comment is that according to the longer coherence time of the nuclear spin, the sensitivity enhancement is more or less expected, and we obtain this kind of sensitivities. And as I mentioned, this line corresponds to the prospect of other possible approaches. And this region actually corresponds to the Comagnetometry. So I think it is something like this. So less than some mass range here, but it is comparable in this region of the mass. Also, there's a storage ring constraint and Cascade gradient constraint here. And I think the interesting mass range for our prospect is something in between the Cascade gradient and the storage ring.
I think it's even potential 12, I think the 20 people potential 20 here. I saw those numbers motivated by the previous setup on the diamonds. Is this system, oh, it's the same?
No, this is the same, yeah.
System.
Using the same system, we are using the nuclear spin of the nitrogen. That's the idea.
You say that the nuclear spin has a longer relaxation time,
Yes.
but does the electron spin relaxation time not matter?
Oh, that's a good question. Actually, the longitudinal relaxation time, T1 of the electron matters. If there's a T1, and actually this 7 millisecond is limited by T1. If we wait for T1, like millisecond, then some random spin flip of the electron spin occurs. Then it creates an inhomogeneous magnetic field as a function of time, and that dephases the nuclear spin state.
But now it's the T1 of the electron, not the T2 of the electron.
Not the T2. T2 is irrelevant for our Ramsey sequence, for example. If we start from the Bell state, for example, then there's an extra factor coming from T2 of electron. Then the sensitivity is limited by T2 electron. So it depends on the state, I think. Okay, very brief final comment on the comagnetometry because there was a question. Using this kind of setup, using nuclear spins, I would like to propose this kind of protocol for the DC magnetometry, comagnetometry. It's a little bit different from the usual comagnetometry, I know. But we can artificially make a cancellation between the electron spin interaction part and the nuclear spin interaction part by using this kind of protocol. The idea is we perform the Ramsey sequence for neutron spin, nuclear spin, the Ramsey sequence for electron spin, and here is a swap gate, which swaps the quantum state of the electron and the nuclear spins. So according to the swap and these two gates, the consequences of the Ramsey sequence are adds up with each other. And if we choose a very fine-tuned choice of the ratio of free precision times for here and here, we can obtain the cancellation of the ordinary magnetic field effect to the nuclear spin electrons. But similar to the usual comagnetometry, because the axion-induced magnetic field has different interaction ratio, this effect is not cancelled with each other. We can be sensitive to this axion signal yet. What was the comment? Yeah, that's the idea, basically. And okay, I remember that. This kind of protocol is, of course, interesting for us, but it is not motivated at all in the context of usual quantum sensing because this protocol is insensitive to the magnetic field. So I think it is interesting for us to propose this kind of fancy protocol to look for axion or dark matter signals in the context of particle physics. Okay, let me summarize. I have proposed a way to use enemy centers to look for weak magnetic field-like signal. The benefit of the enemy centers are like the wide dynamic range and the sensitivity scalability with enhanced statistics. Some application of the advanced quantum methodology techniques is possible. It might be interesting to think about entanglement or comagnetometry or something like that. And we are now setting up an experimental environment according to the cryogenic temperature environment. Okay, that's it. Thank you.
Here, questions?
Thanks for the nice talk. I have a question. If you don't use, let me say, this diamond device, Are there other alternatives to do this process?
I mean, I don't know very much about that. Similar. Yeah.
What is the advantage of this diamond without the nitrogen? I mean, in comparison with other atomic systems, maybe a transistor which has a defect, for example, I don't know.
This is well researched, this LED diamonds as my magnetometers, so but nobody applied, I mean, like it's being a rage in the last 10 years, and this AMO stuff.
Yeah, as far as I understand, one of the benefits is this wide dynamic range coming from the possibility to manipulate the quantum system totally. And yeah, but I'm about that. I don't know.
But people use other magnetometry for I have a follow-up question. Has anyone observed the so-called Signac effect using this NV diamonds?
Sorry, what kind of effect did you say?
It's called Signac. It's a coupling of spins to the rotation of the Earth. So at the microhertz level, with any precision experiments using atomic magnetometry at some point at the microhertz level encounter the fact that the lab is in non-inertial frame, and there is a microhertz contribution to the spin precession of anything that has spin. So
it's sensitive to this thing.
oh yeah, beyond that, right? So the friend of mine had to take his Mike Wallace had to take his apparatus to the South Pole, where like almost doesn't have thing, right? And so so there is I guess there will be depending on how your quantization axis orients itself relative to the rotation of the Earth, probably you can sort of see the variation of the precession frequency of this level.
I see. That's an interesting idea.
I don't know how that can be measured.
Well, this is measured in many systems. Yes, absolutely.
For magnetometer system, they don't put it all like kind of parallel to the ground, right? So they have this
I have to like read back to it, but it's one of the effects that is well known. It's very small, but it's measured.
I'm gonna run because in that case, like they usually polarize those kind of molecules in one direction, right? But so then you can just make your experimental apparatus such that you don't have a lot of noise coming from this oscillation. In this case,
you use a gyroscope or something like this.
Maybe.
Yeah.
Yeah, I was just wondering. In their case, like they have specific direction, but in this case, they have direction, so maybe you don't take. Yeah, I think it's good background.
No, it's just a question if this is ever going to be an important tool for precision, that like measuring ever small interactions. This is a Signac effect is the first thing obvious targets.
And here they're integrating over like microseconds, right? Which is like.
Well, the atomic magnetometry also has well, analysis thing as like apparatus, right? Beyond that, so they keep repeating, right? And then they're looking for abnormal sort of 24-hour modulation of the signal, but there is on top of this there is contribution, right? But I don't think it scales the same way. It doesn't scale with gyro magnetic factors. That's why they pick it up. Again, it's just a gravity. Not gravity, but then non-inertial system.
Yeah, to be honest, I don't know the papers regarding that topics. There are some papers discussing the fifth force search using element center, for example, and yeah, and something similar might be in the literature, but I don't know.
Can we go to any of your sensitivity blog?
Neil, okay.
Maybe ask, what did
Yep.
you include there for your noise?
What is, sorry?
What did you include there for your noise?
Spin projection noise.
Just
That's
a
it.
single source of noise. You know all the other source of noise, that many operations you have in your typical readout, right? These are operations in your quantum system. You assume they are all noiseless. They are noiseless. So in some sense, this is really an idealistic theoretical projection.
In some sense, yeah.
The best ever achievable.
Agree.
So have you ever compared with any realized system with even just a single NV system? What's their noise spectrum? Do they agree with your estimation, or they differ by 5 orders of magnitude?
I mean, they are now improving the sensitivity to reach the spin projection noise, and still not yet, just a little bit above the spin projection noise. And a factor of 90 is actually the deviation from the spin projection noise now. But yeah, I heard from the professional of this kind of topics that yeah, the field is fast improving.
We reject several operations.
Oh yeah. This is the common way to do for magnetometry. So
when you say you have any potential 12 or 20, you just assume I have individual incoherent NV centers. I can have signal, so you didn't collect the light coherently. You assume incoherent.
I don't think so. To some extent, we can make the coherent initial state, for example, by irradiating the sample with green light, and then when it comes back to the lower energy state, it is in the ground state. Then we coherently start from this state. Then if the applied magnetic field is coherent for whole lattice, then the quantum state evolution should be coherent.
So in this game, you assume all coherent preparation and readout for your system.
Basically, yeah. At least for this sensitivity, in order to reach this sensitivity, there should be. Yeah.
Yeah, I could have another question about the protocol. So you have this whole complicated protocol of high pulse, but you let it evolve for a little bit of time, but there's a lot of overhead other than
Oh yeah.
The observation time is really just when you let it evolve. Do you have a sense of like what the overhead versus useful time is?
That's a good question. Comparable. As far as I remember, the state initialization takes like 1 microsecond, and the readout takes like less than 1 microsecond, 0.4 or something. So comparable. There should be some other one factor here. But yeah, that's the situation.
So, thank you.
Thank you.